So bird strike, high impact with a jet aircraft can cause a lot of damage. The amount of energy that a 5-kilogram bird, about 11 pounds, traveling at 275 miles an hour, or 171 miles an hour, is the same amount as a 100-kilogram, 220 pounds dropped from 15 meters, or 50 feet, 49 feet. So if you took 220 pounds and dropped it 50 feet on top of an object, that's what a bird does to an aircraft that's traveling very quickly.
Oh, they go that fast?
Pardon me?
They fly that fast?
The bird doesn't, but the airplane does.
Airplanes fly at like close to 300, some of them don't.
Some of them do, yes. So what we've invented, well, at first what they had is they literally had a cannon, a chicken gun. And they would take frozen birds, and they would turn the engine on, and they would shoot the bird at the engine to see if the engine could take it. Because an engine is supposed to it's supposed to be able to withstand one 4-pound collision, and the tail has to withstand something else. The cockpit windows, they have to withstand a 4-pound bird without yielding, without breaking. So they have to test these things. But, you know, that even gets expensive. You can imagine having bird duty and going out with your cannon and shooting the cannon at the engine, and if it breaks the engine, you got to build another engine. So I guess where I'm going with this is you kind of wish you had some sort of model, something you could do on paper, which you could calculate what a bird would do to an object without having to build the object or kill a bird. So here's a paper that I thought was kind of interesting. Finite element analysis of bird strikes on composite glass panels. This is from Kochi Chuan, Department of Mechanical Engineering, the University of Singapore. So this is another typical research that is going on right now. And finite element analysis is fancy for breaking things into little pieces, right? So instead of looking at the big airplane and saying, what happens when a bird hits the entire airplane or this engine, right? We take it and we map we break up the face of the airplane, the object, and we build little squares, and we say, well, what happened if something hit this little square? And there would be a force here, and a force here, and a force here due to the impact on the square. And then this force would in turn generate a force on the square next to it, and this one would generate a force next to that. And there's an equation, a very simple equation that we can use to calculate how this force affects this pin, and how this pin affects that pin. And eventually you can build a picture of the airplane with all these little pixels, finite elements, and you tell the computer to add up all these little stresses and strains, little forces, and it can predict the overall picture of how a bird is going to affect the airplane without having to build the airplane and shooting birds at it. Finite element analysis. I didn't want to show it to you really because that's super complicated and it's not very interesting. But I did want to show you the next aspect of historical flight. Once you know you can fly, and once you know you can carry things, the next question is, how do you fly fast? And that means you need to have something that pushes you fast. You need an engine. So here's how engines work, basically. It's a big tube, a big can. And at the front of the can, you got this thing called a compressor. And just a basically rotating fan. And as the air goes through the compressor, guess what it does? Wild guess.
Compresses air.
Okay, that's pretty good. It compresses the air. It packs it into a smaller volume. And it sends this compacted, pressurized air into a chamber where they put a little fuel. They mix up high-pressure air with some fuel, and then they light it. And it blows up. Boom! And all of that energy is directed towards the back of the airplane. So it's hot, and it's fast, and it's being blown out the back of the airplane. On its way out, it goes through this other fan, that's one called a turbine, and it pushes it. The air that moves through the turbine turns the turbine, and the turbine is connected to the compressor, so the turbine turns the compressor, and the compressor compresses the air, and it blows up, and it turns the turbine. It's sort of this self-perpetuating cycle. The rest of the air gets blown out the back, which means that the rest of the engine gets pushed forward, and anything that's attached to it goes forward. But that's basically how airplane engines work. The best airplane engine has really high pressure air. And most often, one compressor isn't going to do the job. You need a series of compressors. So you compress the air a little bit, then you send it to another compressor, and it compresses it, and so on and so on. And then you blow it up. Okay, well, there's a whole science to compressors. I guess I'll talk for another 10 minutes, or I don't know how much time I have.
Till 6.
But here's the equation. Pardon me?
I said not till 6.
Till 6. Tomorrow. All right, so the force that's generated by an airplane is equal to, there's this little m dot, which is, again, another derivative. You can't see the equation, but I'll just try to write it up here for you. The force that's generated, the thrust by this aircraft engine, is how quickly the mass is moving times gravity times this thing called the specific impulse, which is how much kick per unit of fuel. So a big science in combustion is how do you make a fuel that's light and that has a lot of energy when you blow it up. So that's called the specific impulse. And what you want to do is subtract sort of a drag, literally, the area of the exit hole times the pressure outside the hole. So you need to take that away from the thrust generated by exploding mass that's moving very quickly at a specific impulse. So that's the equation that essentially dictates how much force you can generate by one of these engines. But what the part that I thought was neat is this aspect of compression. And when you have an engine, I told you that it takes many stages of compression to get a nice high pressure pack of air. So what happens is, at the very inlet, what direction are they going? Well, let's see. I'll just talk about it here then. Let's see. At the very inlet, these are called stator vanes or stator nozzles. The entire thing is a nozzle. But these vanes are not moving. They're just out in front of the aircraft, and they're directing the air onto the compressor. Now these vanes are moving. They're moving upwards in that direction. And the best flow that you can get from one vane to the other is when the air... Oh, I'm trying to draw it upside down. Let's see if I can do it. Okay, so this one is on the rotor. This is a blade on the compressor. The best flow that you can get, the most efficient flow, is when the air lands at the surface of that wing, they're essentially little wings, and flows nice and smooth across its surface. So you want to send the air right onto this moving blade so that it goes on there flush. And you can see right now that it doesn't look like it's going to be flush. It looks like the air moves out of this directory vane and it hits the backside of the moving rotary blade. That's what it looks like. But the truth is, this is a rotary blade and it's moving. So actually we have relative motion. What we want is not what the air is actually doing. What we're considering is what the rotary blades think the air is doing. We want the rotary blades to think the air is moving in this direction. It's a relative velocity. So what I've drawn here is this line represents the speed of the vane going perfectly upwards. This line, this little line right here, is the direction and speed of the air that's moving off the stator blade. And the difference between those two velocities is called the relative velocity. So I don't know if you can see it in red, but the difference between those two arrows is an arrow that is lying flush to the surface of that vane. So there's a science to how are you going to angle these rotary blades, or the stator blades, so that one blade feeds the air nice and smooth onto the moving blade. That's a big deal. And if you get separation inside of here, if that flow is not smooth, you get a lot of drag on these little wings.